1. So it's another way of saying plus or minus 1. Let's just take an electron, put it in a region where it would have this 1 volt, I think 9 volt battery, 1/9 of that. Put it in that location relative to something else, and we would say it would have 1 electron volt. What is an electron volt? Well, take the energy. 1 electron volt corresponds to, here's a weird coincidence, 1.602 times 10 to the negative 19 joules.
Okay.
So that answer ends up being, you take this number and convert it into electron volts. Just a weird unit, you look it up in the back of the book. It's not all that necessary, but I want to tie this even further to chemistry. Joule units cancel out. Got a power of about 10, so it's about 13, 14. Electron volts, give or take. Basically 2.3 divided by 1.6, multiply that by 10. Maybe not quite that, might be half of what I'm thinking. Is it about 7? 14.4? So this energy, it's about 14, because I was right the first time, I started second guessing myself here. 14.4 electron volts. I didn't know exactly what it was, but I knew it was sort of in that ballpark. If you kept your general chemistry book, go back and look at the ground state energy of a hydrogen, of an electron in a hydrogen atom. You know what the number is? It's a negative sign. Kinetic energies can never be negative, so it's actually a negative energy with the ground state of the electron. If you look at the number very carefully, it's about 14 electron volts. This number, which you can derive from just simple physical requirements, corresponds in a very close way with the known energy values for an electron in a hydrogen atom. That's one of the first triumphs. This is a beautiful, there's a paper on this. One of the papers for our projects is on this analysis and this idea. But the point is just, okay, that's not so much energy. 14 electron volts. It's 14 units of energy on an electron scale.
So that represents the excess, you say?
No, even better. That's the requirement for how much work the electric force would have to do to take an electron that wasn't moving, accelerate it to this speed, and into this orbit. It would take that much work. Oh, now we're back to work. Work, energy, kinetic energy, force, acceleration, it's all tied in together. So that's work. That's what the force does. Changing kinetic energy is taking your net work on the... So if you started from rest, that's how much it would take to get it there. And how much energy it would take to yank that electron off of there and bring it back to rest. Wild stuff. Okay, so briefly, we had about 6-7 minutes left. Let's just take this simple little model and extend it a little bit farther, because I want to now look at what happens when we have more than just 2 charges interacting, because that ends up being sort of the next obvious extension, right? Nature just doesn't have 2 charges sitting out in the vacuum. Be 3, 4, 5, 6, 7, 8. So let's just look at let's extend this little nuclear idea and put an electron somewhere else and see what that would do to the dynamics of an atom. Okay, so this would be now example number 3. So now we have 1 positive charge and 2 negative charges. Here's the positive charge, and over here was that negative charge, and we said that distance was 5 times 10 to the negative 11. And let's put some Q1, Q2, And let's put at the same distance over here, let's put Q3. Yeah, same distance away. Now there's going to be two parts to this question that I want you guys to think about, and we're not going to get through that today. Here's what I'd like you to think about. First of all, at this distance, what is the force on Q2? First question. What is the electric force on Q2? Now, if they're moving, assume that they're moving so they're always on opposite sides. Now, that's not realistic, but I want to start there for basis of discussion. So, question 1. What is Fe on Q2? Second question. If we can accept, big acceptance here. If we can accept that the electric force required to keep a stable electron doing its little thing around the atom is this amount of net force, what would the radius of Q2 and Q3, what would the distance of separation of Q2 and Q3 need to be relative to the nucleus in order to maintain that same value? So the second question is, if this is D, and call this distance R, and this distance R, I'll write it in here so it's a little bit longer. So, assuming that they maintain the same distance apart, what would this distance need to be to keep that same orbital force and kinetic energy on this electron? This is what somebody would have to have done in 1915 to validate this electron model of the atom. This planetary sort of model of the atom. So, these are the questions. And see if you can set that up and work on it. Just work on it for a few minutes together. And let's talk about it at the beginning of the lab on Friday. And see how we set it up and how we can come to some consensus. Pretty deep class. A lot of things in the gaps. Textbook just kind of lays things out, and you forget just what this stuff really means. And I think that's kind of where the cool part is. You really sort of see how it all ties together. I never understand why people don't try to spend more time reading it. So while you guys are together, work on it, talk. I mean, that's a good thing to do while we're together. How do you
Stuff,
set
dude.
it up?
That's how we did it on the worksheet.
Coordinate.
Fe equals negative K Q1
Yeah, we can
Q3.
treat them separately. Let's say I take this as an origin, so we can calculate the force from
Okay.
here to Q2, and then take this as an origin, calculate the force from here to Q2, and then find the net.
Yeah, okay. I reversed that. Yeah, that's
Does both sense?
yeah. No, we can do it that way. Yeah.
I just take them separately as well.
Yeah, we have if we just take Q3 distance down 5 times 10 to the negative 11.
What is the
K.
Q2 squared. So we have
Q1, Q2, like that.
Tell me, do we want a positive or negative value there?
Or here?
Yeah.
Well, notice I just left it not as an arrow, but just as a magnitude. So it technically would be negative as a vector in this particular point, but rather than get too caught up in the need for it being a vector, we can just treat it as a
R over here
magnitude,
is
as long as
double
you
the
keep the signs
size.
right for the individual forces.
I didn't notice that there was no arrow there.
Q3.
So they just take the same quantity chart.
Might just be some algebra.
Oh, yeah. Absolutely.
That's cute. I gotta relabel this.
Go, go, go.
When we did this first one, what, Q2 was going opposite X direction. When we did it first time. Or did you try that? First time it's only repelling each other. Second time it's only repelling each other. Yeah. Because now we call the FE a negative, and that went to 3 because it keeps it going. It was direction. So that's the, say it's negative 1.6. That's a cycle order. Yeah, positive, negative. So if we something's like 1.6, something keeps you going up and down, right? So go forward in the negative direction.
I think we simply got this.